The candy.
All right, hi everybody. Let's see. So we are going to continue working through chapter 10 today and tomorrow. And that's we're talking about potential energy. And so that should get you ready for your homework over chapter 10 that's due this coming Sunday. And then next week we will jump into chapter 11 and talk about the concept of momentum. Okay, so let's just jump into the slides straight away. Okay, and I just want to start with a example problem with a system where we have to consider conservation of mechanical energy. So remember yesterday we introduced the concept of a potential energy, that somehow it's energy that gets stored inside of a system as the configurations of the objects inside of the system are altered. And there are two specific examples that we looked at for gravitational potential energy, right? We saw that for a massive object that's separated from the Earth, the gravitational potential energy is like mgh, where h is mgy, where y is its vertical position. And we saw that for, say, a spring system, the spring potential energy was 1/2 the spring constant times the stretch of the spring squared, something like this. So let's look at this example. Let's imagine that we have two balls or two objects, and one is twice as heavy as the other, one is twice the mass. And we're going to go up to the roof of a building and drop those two objects off the roof of the building. We're going to ignore any air resistance here, so we're not going to consider any non-conserving interactions where there could be changes to the thermal energy of the system. Just before the two objects hit the ground, okay, the heavier ball has what fraction of the kinetic energy of the lighter ball? So how will the kinetic energies compare? So let's see. Let's make a quick diagram. We have one ball that's mass m. We have another ball that's going to be twice as massive. They're going to start at some height h above the ground. And so this is the initial condition of the system, and they're both going to start at rest. So they're both going to have some initial velocity that equals to 0. Then after some time, we're going to observe that both balls have fallen and reached the ground, and they're going to have some final velocity. Right? Those final velocities we know are going to relate to the kinetic energy of these objects, right? We know the kinetic energy is like 1/2 mv² for these objects here. How do the kinetic energies of those two objects compare? Well, let's try to understand that from an energy conservation perspective. So let's think about the energy. So for the object that has mass m and the object that has mass 2m, the initial energy in the system, right? Those objects are at rest to start, so they have no, so the initial energy we're going to say is the initial kinetic energy plus the initial potential energy. We see the object is at rest, so it has 0 initial kinetic energy, but it starts some height h above the ground. And yesterday we convinced ourselves that we're free to choose our coordinate system and where the origin is. So let's just pick a coordinate system where the origin starts at the ground and y is increasing upwards as I go upwards from the ground. So in that case, the initial potential energy is going to be like mgh for this object. What about the mass, the object that's twice as massive? Well, the same idea. I can find its initial energy. It has no kinetic energy because it's at rest. Now it's got twice the mass. So look, the mass comes into the potential energy. So it has twice the amount of potential energy. That means this object has twice the amount of twice the amount of total system energy to start. And then what's going to happen as the system evolves, we can look at what happens in the final state. The final energy is going to be the sum of the final kinetic energy plus the final potential energy. And here we can see that the final potential energy in this coordinate system that we've chosen is just going to be 0 because it's at the origin that we defined in the coordinate system. And so we can write down that this has to be 1/2 the mass m, because I'm looking at this mass little m, times that final velocity squared. And this potential energy piece is going to go to 0. The final energy on this side has to be 1/2 2m times that v final squared. Okay. And now we can see that this final energy, right, all of the final energy is just kinetic energy. And we know that the energy is conserved, so this initial energy has to be equal to the final energy. So I can see all of the initial energy that I started up with has to end up with kinetic energy. So I could have done this without writing down the functional form of the kinetic energy. I can just argue that since the mass the object that's twice as massive had twice the amount of initial system energy, and none of it was kinetic energy, that by the time all that gets transformed in kinetic energy, the object has to have twice the kinetic energy. And I can see that explicitly from the functional form that the heavier object on the right has to have twice the kinetic energy because of the extra mass here. Okay. How do the velocities compare for these two objects? How do the speeds compare? What do you guys think? How will the speed of the two objects compare just before it hits the ground? Well, let's see. Let's use our energy conservation to check. For the mass that's just a single m, our energy conservation says that initial potential energy, mgh, has to equal the final kinetic energy, 1/2 m v final squared. The object that's twice as massive had twice the amount of initial potential energy, and its final kinetic energy would be 1/2 m, or sorry, 1/2 2m v final squared. Now notice that in this equation, the two mass terms cancel out. And you can see that in either case, I'm left with the same functional form, that final velocity, right, in either case would be equal to the square root of 2gh. Now we already knew this from our kinematic equations, right? Both objects would be experiencing the same acceleration. They started with the same initial conditions, and so I should end up with the same speed or velocity by the time the object reaches the same point, right, if it falls. And I can get that same result from this energy conservation expression. Okay, let's try a few quick check problems to see how we're doing with this. So let's imagine this, that I have 4 different slides. They're all frictionless, and I'm going to send a child or an object down each slide. And in each case, what I'm going to do is I'm going to start the object at the top of the slide with 0 initial velocity. Okay. In all cases, it starts at rest. And then what I'm going to do is I'm going to look, and I want to know something about the speed, right? They're going to end up with some velocity at the bottom of this ramp. And I want to think about the speed, the magnitude of that velocity when the object gets to the bottom of the ramp. How does the speed compare for the box or the child that slides down these different slides as they get to the bottom of the ramps? I'm gonna give you guys about 10 more seconds. All right. So the most popular answer was D, that they end up with the same speeds at the bottom of the ramp. Okay. That's our correct answer here. The answer here is D, same speed. How do we know that? Well, look, each object has the same initial energy. All the energy initially is in kinetic energy, mgh. They also each end up at the same final position down here at the bottom of the slide. So the final energy here will have used up all the potential energy, and I'll just be left with kinetic energy 1/2 mv final squared. And through energy conservation, I can say that that initial energy has to be equal to the final energy. And so no matter which slide I pick, I'm going to have an equation that says that mgh is equal to 1/2 mv final squared. And look, this tells me that that final speed for the object, again, is the square root of 2gh. And this expression has nothing to do with the shape of the slide, right? It just depends on where I started and where I ended up, and nothing about the path that the object takes in between those two different steps. So this is an example of a problem that's very easy to solve this using energy conservation. This would have been challenging to solve using kinematics, right? If I had asked you to start that the initial velocity is equal to 0 and then to find the final speed, okay, using kinematics, well, what's the problem here is that the acceleration for many of these slide shapes, the acceleration is going to be variable as I move down that ramp because the orientation of the slide is changing, right? And the component of gravity that points in the direction tangent is going to change. And so I would have to find the functional form for the acceleration and do the integral, right? And have some complicated equation to find for these two curved pieces what that final speed would be from kinematics. But from energy conservation, it's a one-liner and we can see that those two objects have to end up with the same speed. Now it's a different story if we want to know the different components of the velocity, right? Just from the acceleration. We could use the constraints, right? That we know that it has to emerge tangential to that. We could just use the geometry of the slide. But if we wanted to infer that from the acceleration, well, right, to get information about the directionality of the velocity, we would still have to go back to the accelerations here. But if we just are after the speeds, we can use these energy arguments that we're making in this chapter. What about this one? If I have a child that's swinging on a playground swing and their motion, right? We know that as they swing back and forth, they're momentarily motionless at the highest point of their arc that they're making. What is the energy transformation that's taking forth as they swing back and forth down to their lowest point of motion? Let's go ahead and end this one. Most of you picked B, that we have conversion of gravitational potential energy to kinetic energy, right? Absolutely. We have a swing here. We have this person sitting here on the swing. We can think about them like a mass on the end of a pendulum here. They have some zero initial velocity here. By the time they swing down to this position, right? Notice that their height has changed. They've changed in height by some height h. That means they've lost potential energy. So the kinetic energy here at the bottom of the ramp, let's call it kinetic energy final, is going to be equal to that initial potential energy that the object has. So all that initial potential energy that got lost as I dropped in height on this swing system gets converted into kinetic energy. And now I have some velocity, right? As I swing back up, that kinetic energy is going to get transformed back into potential energy until I run out of kinetic energy. And that means that the maximum height I'm going to reach on this side again is just going to be h, because I know that's the height that I reached to use up all that kinetic energy that I had at the bottom of the ring. What about this one? What about a skier that's gliding down a gentle slope at a constant speed? Okay, let's go ahead and end this one. Most popular answer here was D, that it's potential energy converted into thermal energy, followed by kinetic converted to thermal. Right, as the skier is going down the hill, they start here at some initial position. Later, we find them further down the hill. They're maintaining a constant speed. So there's some initial kinetic energy, and then there's some final kinetic energy, but because the velocities are the same, we know that final kinetic energy is equal to the initial kinetic energy. That tells us that the change in kinetic energy is equal to 0. But we can see that this skier is going to drop some height h as it goes down this slide. So that tells us that the change in gravitational potential energy is less than 0, right? I'm losing gravitational potential energy as I go. Where did that extra energy go? Right, it went into the thermal energy. The change in the thermal energy then has to be positive to pick up that extra energy. And so this is a case where I'm taking gravitational potential energy and converting it into thermal energy. So let's see if we can calculate, right, use all these ideas of potential energy and the idea of work that we saw in the previous chapter and add back in the possibility that I can have thermal energy acting inside of the system, right? We wrote down an equation yesterday that if I have some initial kinetic energy and some initial potential energy, and there's some work being done by, say, some friction, that has to be equal to the initial kinetic energy, or sorry, the final kinetic energy and the final potential energy. This work done by friction is going to be my change in my thermal energy. So let's see if we can do an example like this. Let's imagine we have a block that's sliding along a frictionless horizontal surface with a speed. Oh, sorry, I'm jumping the gun here. We're not introducing friction yet. We'll do that momentarily here. In this case, we're still going to look at a frictionless surface here. Let's imagine that I have a block sliding along a frictionless horizontal surface, and it's going to collide with a spring and compress the spring. What's the maximum compression? Sorry, I'm goofing this one up, guys. And the maximum compression is found to be 1.4 centimeters. It says if the same block then collides with a spring while having twice the speed, how does the maximum spring compression compare? Okay, so in this example, we're going to, again, take thermal energy equal to 0. So that tells us we're going to have conservation of mechanical energy, that the initial kinetic energy plus the initial potential energy should equal the final kinetic energy plus the final potential energy. What kind of potential energy are we dealing with here? Well, we're talking about a spring system. So we're going to have to consider the spring potential energy 1/2 K delta X squared. What does this problem look like? So here I have a spring that's, say, attached to a wall, and I'm going to have a block that's sliding towards the spring with some velocity v. And then later, right, this is the initial configuration. Later, I look at this system and I find that that spring is now compressed by some amount, and the block has momentarily come to rest, that the velocity is equal to 0, but we can see that there's a displacement, right, a delta x associated with that spring system. The spring has been squeezed in and its length is changed by some distance that we can describe as delta x. We can write down an energy conservation equation here. In that first case, we can see that the kinetic energy is 1/2 mv squared. And the spring potential energy in this case would be equal to 0 because the spring has no displacement from its equilibrium length. In the final case, we can see that we have 0 initial kinetic energy, but we have some 1/2 K delta X squared worth of spring potential energy. And our energy equation tells us then that that initial kinetic energy, 1/2 mv squared, has to equal that final potential energy stored in that compressed spring. So the question is, what happens to the compression, the delta X, if I give the block twice its initial speed? What's going to happen? Well, let's see. If I increase the velocity by a factor of 2, right, the thing on the right is going to change. This is going to be 1/2 m times twice the velocity squared. It's going to have to equal 1/2 K delta X. Let's call that delta X prime. That's the new compression squared. And here I can see on this side, right, that this 2v is going to have to relate to this delta X here. And so I can see that I'm going to end up having to have twice the amount of compression as the spring, right? To get this, if I have twice the energy here, if I have twice the speed, it means I'm going to have 4 times the initial kinetic energy. That means that I'm going to have 4 times the final spring potential energy. To get 4 times that final spring potential energy, I'm going to have twice the amount of compression on the spring. So you can see from this relationship that this has to be twice that spring compression from the first case. And so this has to be something like 2.8 centimeters. What happens if I have that same problem and I'm going to replace the spring now with a spring whose spring constant is twice as large? How much will that block that's going speed v compress the spring by, right? So we saw that the first case I had a block going by v produced a delta X that was equal to 1.4, what was it, centimeters. Okay. If I double the spring constant, what's going to happen to the squeeze, right? In this expression, we said 1/2 mv squared was equal to 1/2 K delta X squared, where delta X was my squeeze. And now I'm saying I'm going to keep the object with speed v. So in the second case, I'm going to have 1/2 mv squared. I'm going to have the same amount of kinetic energy. But now I'm going to double the spring constant. So I'm going to have a new spring constant that I'm going to call K prime. That's going to produce some new amount of squeeze that I'll call delta X prime squared. And I know that K prime is equal to twice K. How do the speeds compare? Well, let's plug that in here. So let's see. this expression plus this expression tells me that 1/2 mv squared has got to equal to 1/2 times twice k delta x prime squared. And I know 1/2 mv squared from this expression is just equal to 1/2 k delta x squared. And now I can solve this equation for, right, I get the halves canceling out, the k's canceling out. And I get something that says that 2 is equal to, the square root of 2 is equal to delta x over delta x prime, right? The ratio of these two things are like something like the square root of 2. So when I get this stiffer spring constant, the compression isn't as great, and it goes like a factor of square root of 2 because the spring compression is inside of this square in the spring potential energy. All right, let's think about this one. Another system where I have a block and a spring. Let's imagine I have a 200-gram block that's on a frictionless surface. It's pushed against a spring, and the spring constant of that system is known. It's 500 newtons per meter. And I compress the spring by 2 centimeters, and then I'm going to let go of the block. What's the speed that's it's going to shoot away from the end of the spring with? What's the speed that it's going to shoot away from the end of the spring with? Let me give you guys a second. Why don't you guys try to work through this one yourself? See if we can see if you can calculate using our energy conservation rules, the speed that the spring is going to fire away with. I'm going to give you guys maybe like three minutes to work through this one. If you come up with an answer, go ahead and share it in the chat, and we'll see how we're doing on this. Try to use the steps we've described so far. Draw your picture of the system initially. Draw a picture of the final system. Write down the energies, kinetic energy, potential energy in both cases, and use the energy conservation relationship to equate them. Okay. See one answer coming in, 100 meters per second. Square root of 50. I'm gonna give you guys like one more minute and then we'll work through this together. All right, let's try to work through this together. Let's make our diagrams. We need to think about the initial condition of the system and the final condition. Let's put the initial condition at the top here and the final condition on the bottom. What does the initial system look like? Well, I have a wall that has a spring coupled to it, and there's a block that's set against this spring. Block has mass m, and I know that that spring has a natural length that's say here, and it's compressed by, right, that spring is being pushed inwards by 2 centimeters. I also know the spring constant for this spring is 500 newtons per meter. What does the final picture look like? Well, in the final case, that spring, here's the wall, that spring is now extended out to its natural position, and that block is speeding up and it's going to be moving away with some final velocity v. And as the spring passes through its equilibrium position, the block is going to lose contact with the spring. How do we know that? Because as this, if the spring moves a little bit further, the spring system is going to extend and it's going to slow the end of the spring down. And so the block is going to continue to move freely and lose contact with the spring. So let's do an energy conservation relationship here. The initial system energy, it's going to be the initial kinetic energy of that block plus the initial potential energy stored in the spring. The block starts at rest, it's just sitting there. So there's 0 initial kinetic energy, and the initial spring potential energy is 1/2 K times that displacement, delta K, delta 1/2 K delta X squared. What's the final energy look like? Well, now the spring system is back to its equilibrium position. So the block is going to move off with some kinetic energy 1/2 mv squared, and the spring potential energy will have gone to 0. My conservation of mechanical energy tells us that that initial energy, system energy, has to match the final system energy. So I end up with 1/2 K delta X squared. It's got to equal to 1/2 mv squared. The halves cancel out. So I end up with that final velocity, right? The speed that that object, or sorry, not the velocity, because we don't know about the velocity here. We can only find information about the speed. The final speed is equal to K divided by M times delta X squared, all of this square rooted. So now we just have to plug in our numbers here. K is 500 newtons per meter. M is my mass, that's 0.2 kilograms in this case. My delta X is 2 times 10 to the minus 2 meters squared. I'm putting everything in standard units here. And so now I just need to calculate this thing. So this is like, I don't know, I'll let you guys plug it in here. This is like 500 times 4 times 10 to the minus 4 over 0.2, or 2 times 10 to the minus 1. So it's like square root of 500 times 4 times 2 to the times 10 to the minus 3, something like this. So 500 times 2 is 1,000, 10 to the minus 3. So this is something like square root of 1 meter per second. Maybe I did my arithmetic wrong there. I got something like square root of 1 square root of 1 meter per second. Okay, so we can use energy conservation to solve, right? And again, this is really nice because all we need to know is about the initial configuration of the system, the final configuration for the system. And very frequently, we're going to end up with a one-line expression that we can write down to solve for these properties of the system and answer things about how the system evolves. What about this one? What if we do a problem where we have a mix of gravitational potential energy and spring potential energy that we have to worry about in the problem? Let's imagine that I have a 20 centimeter tall spring and it has a spring constant that I know, 5,000 newtons per meter. And I'm going to place it vertically on the ground. So here's the ground. I have the spring, something like this. Let's say there's a platform on top of it. And it starts and it's initially 20 centimeters. Its natural length is 20 centimeters high. And then I'm going to take a block and I'm going to hold it 15 centimeters above the top of this spring. So another 15 centimeters up. I'm going to have a block. And I know the mass of this thing is like 10.2 kilograms. And then I'm going to drop the block and it's going to fall onto the top of the spring and it's going to compress the spring. Okay. So this is the initial state here. So afterwards, what does this system look like? Well, the spring is going to be compressed and it's going to be some height h above the ground here. And the block is going to be on top of the spring, something like this. And we want to know, what is that height? What is the height that of the spring at the point of maximum compression? How do I know when I'm going to get maximum compression? When is this happening? What condition am I going to apply to know that I'm at maximum compression? Yeah, Tyler says when the velocity goes to 0. Right, as the block falls towards the spring, its speed is going to increase because it's going to be converting that kinetic energy into gravitational potential energy into kinetic energy. And then once the block starts touching the spring and starts squeezing on the spring, it's going to be converting, right? It's going to be converting that energy into spring potential energy, which is going to take energy back out of the system. And then eventually it's going to store enough energy inside of the spring that it's going to bring this object to rest. And that's how we know when it's going to reach its maximal compression. Okay, so how are we going to do this one? We're going to consider the energetics of this case. Where's the spring compression here? Right? This distance, right? We can look at this distance. That's how much the spring is compressed in the end. Let's call that delta y. Okay, that's the amount that the spring is squeezed when the block is falling down. Let's define a coordinate system that we're going to use to describe the gravitational potential energy. Let's put the 0 at the ground and have y increasing in this direction. Okay. Let's write down the initial energy of this system. The initial energy of the system is going to be the initial kinetic energy plus the initial gravitational potential energy plus the initial spring potential energy. Well, the block started at rest. I'm going to release it from a resting position up here. So there was no initial kinetic energy. It's raised off the ground here. I can see that its initial potential energy then is going to be the mass of the block times the gravitational acceleration constant times the height above the ground. I can see it's 20 centimeters. That's how tall the spring is. And I'm holding the block 15 centimeters above the spring. So this is going to be something like 35 centimeters up above the spring. What's the initial spring potential energy? Can you guys tell me what the initial spring potential energy is? I see 0. Why is it 0? Well, the spring is at its equilibrium position. The spring is not being compressed or expanded initially. So that means I have 0 initial spring potential energy. Now, what's the final energy of my system here? I still have 0 kinetic energy because the block is at rest in the end. How much potential energy do I have? Well, if I called this ground 0, well, now I have this height h, mgh worth of spring potential energy left. And I've got some spring potential energy now because I'm squeezing the spring. So the spring potential energy is going to be like 1/2 k delta y squared, right? That's that squeeze that the spring is providing here. And I can write down then that the initial energy and the final energy have to be equal to one another. So I can see that mg 35 centimeters has got to equal to mgh plus 1/2 k delta y squared. Well, now the problem is I don't know what h is and I don't know what delta y is. What additional information can I use? What additional information can I use? I'm trying to find h, but I need to know delta y. Is there another relationship that I see here? Another equation I can write down? Is there a relationship that you can see between delta y, the compression of the spring, and the height h that the block is? Yeah, delta, so Logan says delta y is 20 centimeters minus h. Right, I can see that the height above the ground plus the stretch of the spring need to equal the original height of the spring. I can see delta y plus h has got to be equal to 20 centimeters. Delta y has got to be equal to 20 centimeters minus h. So I can rewrite this. This is mgh plus 1/2 k, and now I'm going to have my 20 centimeters minus h squared. mg 35 centimeters. And now I have an expression where I know the mass of this object that was given to me. I know the gravitational acceleration constant. I was given the spring constant here. The only unknown here is h. So I'm going to end up with something that's going to be a quadratic expression with respect to h, but I should be able to solve for a solution here, right? You're going to end up with something that's going to that we're going to be able to solve for this h here. Now it's going to be a quadratic expression, so you're going to end up with two possible solutions for h here. How will you know which one to use? Well, you'll end up with a positive h, and you'll also end up with something that's like a negative value of h for if this spring had been either stretched or gets compressed below the ground. And so it's that positive value is going to be the one that's physical. Otherwise, you would end up with either the spring stretched or compressed below the ground, which can't be happening here. Okay. So this is an example where we used energy conservation, but we also had to be a little bit clever and notice that there was some constraint, right? Geometrical constraint that we needed to realize to unlock and relate these unknowns so that we can solve this problem. So if you're working through a homework problem or something in this chapter and you write down your energy conservation equation and it doesn't seem like you have enough information, look back at your diagram and see if there's some constraint that relates some of those unknown variables together, something in the geometry of the system that will let you proceed. Okay, let's try a few quick check problems about spring potential energy here. So let's imagine that I have a spring-loaded gun that's going to shoot a plastic pellet out and it launches the ball with 2 meters per second. How is the speed of that launched object going to compare if the spring is compressed by twice as far? What's that going to do to the launch speed if I compress it by twice as much? Spring potential energy is 1/2 k delta x squared. Okay, let's go ahead and stop this one. Most popular answer here is D, that the speed goes up by a factor of 2. Look, if I double the spring compression, my delta x goes up by a factor of 2. It's squared, so that means the spring potential energy is going to go up by a factor of 4. My kinetic energy equals 1/2 mv squared. If the initial potential energy goes up by a factor of 4, that means by the time the ball launches, its kinetic energy should also be up by a factor of 4. But it asks about the ball's launch speed. How do I increase the kinetic energy by a factor of 4? Well, I have to double the speed because it's also being squared. So the answer here is that I have to double the speed. Let's try this last one for today. I have the same spring-loaded system that's going to shoot this projectile with a speed of 2 meters per second. And now what I'm going to do instead of changing the compression is I'm going to put in a new spring that has half the spring constant. Or sorry, has twice the spring constant. I'm going to put in a stiffer spring. I'm going to compress the spring by the same amount. What's the ball's new launch speed? So all I change is I put a different spring in that's stiffer by a factor of 2. How does that change the launch speed? Okay, let's go ahead and end this poll. All right, we have some results kind of all over the place here. Most popular answer was E though. So if I double the spring constant and keep everything else the same, what's going to happen to the amount of initial spring potential energy? If I increase K by a factor of 2, then my spring potential energy is going to go up by a factor of 2. Energy conservation then tells me that my final kinetic energy, which is coming from the transformation of spring potential energy into kinetic energy, my final potential energy, or sorry, my final kinetic energy also has to go up by that same factor of 2. I have twice the amount of initial potential energy. That's going to lead to twice the amount of realized kinetic energy. Kinetic energy is equal to 1/2 mv squared. How do I end up with twice the amount of kinetic energy? Well, I have to increase the velocity, not by a factor of 2, but by a factor of square root of 2, right? Because the velocity is, because the velocity is squared there. So what's the correct answer here? Well, the speed is going to go up. It doesn't double. It doesn't stay the same. Okay, so those can't be right. So the answer here is that it's got to be C. It goes up to something square root of 2 times that initial speed. Okay. All right, guys, I kept you a bit longer today. I apologize about that. We're going to pick up and finish the last few problems in this chapter tomorrow, and then you should be ready for your homework. Thank you guys so much. If you need to take off, that's all the material for today. If you have any last questions, we can talk about those. For Ricardo, I see you sent me a message. I will send details about written homework 3 probably later tomorrow, or probably tomorrow. But the answer is essentially yes, that the structure is going to be the same, and you guys will be able to work in your same groups for the next assignment. And then also Joshua, thank you. I'll check my email to and respond to you.
I do have a question, if you don't mind.
Yeah, Maram, go ahead.
So like I remember when I missed one session, I made it up, but like you never checked it. Would you check that, please?
Yeah, if those you submitted one of the assignments on Blackboard, Maram?
Yes.
Okay. Yeah, I'll go see if I see a new response there, and I'll get that graded and updated.
Okay, thank you so much. Have a great one.
Yep, you too. All right, is there any other business? All right, if not, then have a great day, and I will talk to you again soon. All right, bye now.